this presentation we are going to look into the concept of data sampling in System Verilog. First let us see what is meant by data sampling. Data sampling is a crucial aspect of functional coverage in System Verilog, which is allowing us to capture the values of variables or signals at specified points in time during the simulation process. This is in turn ensuring us that all the relevant scenarios as well as conditions in the designs are tested. These are the different aspects which we are going to cover in case of data sampling in System Verilog. To start with, we have the individual bins and total coverage. Bins are nothing but it is being used in order to categorize the values of a cover point. Each of the bin is going to represent a range or a specific value of the variable which is being sampled. Individual bins are explicitly defined by the user in order to cover the specific values or range of these values. This is also going to give us a detailed tracking of how often each and every individual value or range of values is hit during the simulation time. What about this total coverage? This total coverage is nothing but it is going to refer to the overall percentage of bins that have been hit during the simulation process. It is going to provide a measure of how thoroughly the design is being tested. If we achieve a high total coverage, it ensures that all the defined scenarios have been exercised. This is also helping us in identifying if there is any gap which is identified during the test plan. Next is regarding creation of automatic bins. So, here is the program snippet for creating bins automatically. So, automatic bins are also called as implicit bins. These are created by the simulator for each of the possible value of a cover point variable. It is going to simplify the process of defining coverage points, especially for variables with a large range of values. Consider for example, if you have a 4-bit variable, the simulator will automatically create 16 bins, one for each possible values from a range of say 0 to 15. So, this is the program example for creation of such bin automatically. So, here we have bit 3 down to 0 mode. So, this is called as a variable mode, a 4-bit variable for which we want to measure the coverage. Next we have a coverage group which is defined as CG. This defines the coverage model and specifies the sampling that is going to occur at pause edge of a clock signal, that is positive edge of a clock signal. Then we have a cover point mode which is going to use the bins auto underscore bins. So, this statement is used in order to automatically create the bins for all possible values of the mode, say from 0 to 15 in this example. So, automatic bins, if they are getting created bins, it is going to simplify the bin creation by automatically generating the bins for all possible values of a variable. These concepts are very much essential in order to achieve comprehensive functional coverage in case of System Verilog, which also ensures us that our design is thoroughly tested as well as verified. Next is regarding limiting the number of automatic bins created. In case of System Verilog, you can limit the number of automatic bins which are created for a cover point by making use of this thing, that is option dot auto bin max. So, option dot auto underscore bin underscore max, here it is set to a value of 16. This setting specifies the maximum number of bins that can be automatically created for a given cover point. If the number of possible values exceeds the particular limit which is mentioned over here, the values are grouped into the specified number of bins. Regarding sampling of the expression, this is an example for sampling of the expression. So, cover point A plus B is the expression given over here. Sampling expressions is nothing but it is going to allow us to capture the values of expression, not just simple variables at specific points in time. This is very much useful for more complex coverage type of scenario. This is the user defined bins in order to find a bug. It can specify exact values or the range of interest. For example, here we have used a keyword called as bin specific underscore values, which is given in terms of 3, 7 and 15. This can help us to identify a specific scenario that might cause bugs. Next is regarding naming the cover point bins. So the cover point bins are named here in terms of low, mid as well as high, which is getting activated for so and so values which are specified over here. Naming the bins is going to help us in identifying as well as reporting the specific type of coverage scenarios. This is also making us easier to understand the coverage reports. Regarding the conditional coverage, here you can see the condition IFF, that is if and only if. This particular conditional coverage is going to allow us in order to collect the coverage data only when certain conditions are met. The condition over here is if and only if the enable signal is asserted with the logical one state. This is very much useful for focusing on a specific type of scenario. How to create bins for enumerated types. So here we have enumerate, enum is the keyword used for enumerated data type, and you have this particular state in terms of idle, run as well as stop. For enumerated types, we can create bins for each and every individual enumerated value, ensuring that all possible states are getting covered. Next is the transition coverage. This transition coverage is going to track the change from one value to another. So it is going to track changes, which is very much useful for state machines or sequential logic type of design. So here idle to run, run to stop, it has to go, then from stop to an idle state. So it is going to track the changes which is occurring in case of a sequential logic or a state machine model. Next is the wildcard state as well as transition. These wildcard bins are allowing us to specify the range or a pattern of values which can simplify the coverage, especially in terms of large or complex state spaces. These are being used. So this is the snippet for wildcard state as well as. Next is ignoring the values. So ignore values. Ignore bins exclude certain values from coverage, which can be useful for values that are not relevant or should not occur. So for such kind of scenario, we can use this particular ignoring values. So here ignore bins invalid for 10, 11 as well as 12 it is mentioned. So such kind of bins are very much essential. Also I can tell that it saves our time, which can be useful for values that are not relevant or should not occur, for which the coverage is not so important, something like that, if I pose a condition on that. So these ignore bins can be used. Next is illegal bins. So for illegal bin, we can mark certain values as illegal. For example, 13, 14, 15 will be illegal in this case, causing an error if they are encountered anywhere during the simulation time. This is going to help us to catch the unexpected or erroneous behavior in a given logic. So here illegal bins error values are represented for 13, 14 as well as 15. Last one is the state machine coverage, which is going to ensure that all states and transition in a finite state machine, that is FSM, are exercised. So this is one example code for state machine coverage. So here we have different states, S0, S1, S2. So the transition is something like this, from S0 to S1, from S1 to S2, from S2 to S0, the transition. So for this you can use a state machine coverage. So we have discussed these different types. These concepts and example will help us to ensure comprehensive coverage during our verification process, which makes us easier in order to identify, also to address any potential issues encountered in our design at any point of time. Hope you understood this concept. Thank you for listening.